So, hello everyone. Let's start today's lecture, live session, I would say.
So, I think you are audible. Just a second, let me share my screen again. Yeah, now it's being shared. So, today is the 12th week and the final week of the control system live lectures. So, I hope you have gone through the lectures of week 12 by Professor Sankaram. So, without further delaying, let's start today's lecture. So, in this week, mostly compensators had been discussed in the class: lead compensator, lag compensator, and lead lag compensators. So, I hope you have gone through all of them, because if I will be explaining all of them, like deriving all the equations, then it will be it will take much more time. So I am skipping that part. I will directly go into the questions. So before going into the questions, I will just want to remind you what is the general structure of a compensator. So in a more like in a control system block diagram. So if this is my control system plant, okay, I will draw it. So if this is my plant or system which I want to control, I want some kind of desired output from it. So this is the output, okay, output of the system, and here some input, okay. What will be the input that we will decide? The input comes from the compensator. There used to be controller, now it's the compensator. So there is a very thin line between what is called a controller and compensator. I want you guys to explore it by yourself, okay. Then this is the some reference signal R of S, and this output is been fed into this, and this is the error E of S. So this is a basic structural diagram of a closed loop compensated system, okay. So now the question come to the question. The question says this part, okay. I will just denote some names. So this is P of S, this is C of S, okay, and whole, let's call it as G of S, okay, open loop transfer function. So now this is called the P of S. So the plant transfer function is given. It is desired that a lead compensator. So remember the lead compensator. What is the for lead compensator? For the lead compensator, what is the transfer function? If you remember, KCS. Sorry, my bad. Kc alpha into 1 plus Ts whole divided by 1 plus alpha Ts, or you can write it as Kc some gain into S plus 1 by T and divided by S plus 1 by alpha T, okay, where my bad, alpha should be in between 0 and 1. So this is the lead compensator transfer function. So what we want, in generally when we design some lead compensator, uh, look at the block diagram. This plant transfer function, plant is fixed, we cannot change anything in the plant. That's why we are introducing the compensator. So in the compensator, our goal is to find the parameters alpha, t, and kc. So if these three we calculate and find out somehow, then we can say our compensator has been designed. Okay, in this question also we need to find out these three parameters basically. Okay, any compensator design questions you will be asked in your exams, be it NPTEL exam or in your classroom study exams or gate, you need to find these three. Okay, so lead compensator. So the question is maximum phase lead. The compensator needs to provide a maximum phase lead of 45 degree. Okay, so now comes, so the compensator needs to provide a maximum. So if you know the formula, I will directly jump into the formula part. So the phi m, if this is the like maximum phase lead that the compensator can give, this comes as I'll write it as sin phi m is equal to 1 minus alpha divided by 1 plus alpha. Okay, that means phi m is equal to 1 minus alpha. Okay, so in the question what's given, in the question given phi m is equal to 45 degree. Okay, that means 1 by root 2, sin 45 is 1 by root 2 is equal to 1 minus alpha divided by 1 plus alpha. That implies what will be the value of alpha, you can calculate. It's 0.707 is equal to 1 minus alpha by 1 plus alpha. Then you need to calculate it. So if you calculate this value, the alpha will turn out to be, I have the answers, solutions, so I'll just write them, 0.172. so you need to verify this. Okay, then the question says if the if the maximum lead, this is the maximum, and this maximum phase angle should be provided at a frequency of 8 radian. So there is a direct formula also for the frequency at which at which it should be the maximum. So that is 1 by root alpha into t. Okay, so that implies 8 radian per second is equal to 1 by root alpha is 0.172 into t. So the t will be 1 by 8 into 0.172. So the t would come out to be t is equal to 0.3 seconds. You need to verify these answers because I am just writing the answers because I have the solutions with me. That's why I am just writing down. So the first question is being done. So what are the answers? The t is equal to 0.3 seconds and alpha is equal to 0.172. Okay, and never forget the units. I have been repetitively saying this, never forget the units. Okay, so next question is, it is desired that the static velocity constant to be 5 second inverse. Okay, then estimate the case. So we know that there is a direct formula for this as well. Okay, it is derived to static velocity constant. So the static velocity constant error, okay, that means that is nothing but the static means what? Just tell me. Static means when the omega is equal to 0, okay, and the velocity error constant. So now coming to the question part B. Okay, so how do we calculate the static velocity error? How do we calculate this? We generally calculate this if of a, like, the transfer function is g of s. Okay, the open loop transfer function is g of s, then this is kv. Okay, that then the kv is equal to limit s tends to 0 s g of s. I hope you remember this thing. So that means in our question kv is given to be 5. Am I correct? Was it given? It's 5 is equal to limit s tends to 0 s into, what is the transfer function? See, first let me write the compensator transfer function. 1 plus ts 1 plus alpha ts, okay, into the plant transfer function 1 by s into s plus 2. I hope this is correct. Let me yeah, 1 plus 1 by s into 1 by s plus 2. Okay, so then we'll just put s is equal to 0. This s will be cancelled out, so limit s tends to 0, then we'll find out to be kc into alpha. Okay, that implies kc alpha is equal to 5. That means kc is equal to 5 divided by alpha. Okay, my bad, there is a 2 here, so this will be divided by 2. I beg your pardon. So this 2 will be also there, so this will be 0, and so this will be half. kc by 2 divided by 2 into 2, that means 10 divided by 0.172, which will come out to be around 58.1. Okay, just verify this answer as well. I might have done something wrong in the calculation. Just verify that whether you are getting the same or something else. Okay, so this kc is 58.1. okay, then determine the low frequency magnitude in dB. Okay, in dB, in this compensator frequency time response. Okay, so what do you mean? Okay, now let me write the, I'll change some pen color. So what is the open loop transfer function? It's kc alpha into 1 plus ts whole divided by 1 plus alpha ts. In low frequency, see, that means omega tends to 0. Okay, and we can write in the prior frequency domain analysis kc alpha into 1 plus t j omega whole divided by 1 plus alpha t j omega. That means when we do the omega tends to 0, look into it, what it will be. When we'll do the omega tends to 0, that means will be the magnitude of g of j omega with okay, we'll do it systematically. So what it will be, okay, let me okay, we can directly say na j omega when omega tends to 0, it will be only Kc alpha, nothing else, because every other terms will be cancelled out. So the Kc alpha, what the question says, what is the magnitude in dB. So the Kc alpha, we know, we have calculated the Kc alpha. Kc alpha is okay. I'm sorry, I have done something wrong here. I have forgotten this part, to include this part. The open loop transfer function means this 1 by s into s plus 2 will also be there. That means here 1 by j omega into j omega plus 2, this part will also be there. Okay. Determine the low frequency magnitude of the compensators. Okay, no, I was correct, because in the question only compensators transfer function is being asked, so it will be c of j omega. I'm sorry for the confusion and all. There is no confusion right now, so this is the final answer. Okay, the question is asked about the compensator only. So the compensator, so j omega. So when the omega tends to 0, the magnitude of c of j omega at omega tends to 0, it will be Kc alpha. Okay, so in the above we know the Kc alpha is 10. That means in dB scale it will be 20 log 10 base 10 is equal to 20 dB. Okay, so the answer will be here 20 dB. Okay, so I'm sorry for the little bit of confusion in between. In the question, you need to look at the question. So what is asked? Low frequency plant's frequency response or the compensator. Here in the question, the compensator's frequency response. It is required. Okay, to have done the first question, let's come to the second question. Second question is also fairly straightforward, I would say. Okay, let me write. It's also a lead compensator. Open loop 0 at -2, open loop pole at -20. So let's write what is the compensator time. Compensator, I write lead compensator. Set a transfer function. What is it? Kc alpha 1 plus ts whole divided by 1 plus ts alpha ts. Okay, also I can write it as Kc into 1 s plus 1 by t whole divided by s plus 1 by alpha t. Okay, so in the question it said 0 at -2 and open loop pole at -20. That means -1 by t is equal to -2 because it's the 0, and the pole is -1 by alpha t is equal to -20. Okay, simple, fair. So 1 by t is equal to 1 by 2. That means t is equal to 0.5. 1 by alpha t is equal to 1 by, so this is 2, this is 20. That means alpha is equal to 1 by t into 20, which is 1 by 10 is equal to 0.1. Okay, so the t is equal to 0.5 and alpha is equal to 0.1. This we have calculated. Then what is asked? The corner frequencies of the compensator. So compensators corner frequencies, we know the poles, the zero location and the pole location. So it's that straightforward. The corner frequencies at minus 2 radian per second and minus 20 radian per second. No, like directly given in the question. So, and the second question, maximum phase lead provided by the lead compensator. So maximum phase lead, we know the formula for the second question, phi m is equal to sine inverse alpha, sorry, 1 minus alpha divided by 1 plus alpha. So what is alpha? Alpha is, so it's sine inverse 0.9 divided by 1.1, which comes out to be, let me see the solution, it's 54.9 degrees. Okay, never forget the unit degree. Okay, then third, the maximum phase lead is 54.9 degree. The frequency at which the maximum phase lead happens, direct formula, we know omega m is equal to 1 by root alpha into t, which will be 1 by root over 0.1 into t. T is 0.5. Okay, so this turns out to be 6.32. What's the unit? Yeah, correct, radian per second. So it's 6.32 radian per second. Okay, so the last question, IV. What's the last question? The value of the parameter Kc at low frequency magnitude of the compensator transfer function to be 0 dB. So when the question says the transfer function's magnitude will be 0 dB, that means in linear scale, in not logarithmic, so 0 dB is equal to 1 unit. Okay, so log 20 log 1 base 10 is equal to 0. That means it asks the value of Kc for low frequency magnitude. Okay, so the transfer function C of S is Kc alpha whole into 1 plus ts divided by 1 plus alpha ts. So at frequency C of j omega, it will be Kc alpha 1 plus t j omega divided by 1 plus alpha t j omega. Okay, that means the magnitude will be what will be the magnitude when, okay, so at low frequency omega tends to 0, that means C of j omega whole magnitude omega tends to 0, it is 0 0 and 1, so it will be Kc alpha, so 20, Kc alpha 20 log Kc alpha base 10 is equal to 0 dB. The question given, that means Kc alpha is equal to 1. Okay, we know what is alpha. Alpha we have okay, then Kc is equal to 1 by alpha, which is 1 by 0.1 is equal to 10. So the Kc, it needs to be 10. Okay, so these two questions were fairly straightforward questions. So now coming to the third question of the week, and which is the last question. So state whether the following statements are true or false. Okay, just by intuition you can answer these questions and comment on your answers. So a lead, what does it say? Lead compensator improves the transient response and amplifies the high frequency. So if you remember, lead compensator, uh, the typical body diagram, okay, the typical body diagram we can see it as uh, this uh, this low frequency. This happens because in the uh, lead compensator, okay, the corner frequency corresponding to 0 comes first, then that of the pole. So this is the corner frequency corresponding to 0, and this is for the pole. That's why the like the body diagram, magnitude diagram, is like this. So you can see as the low frequency, look at it, look at the low frequency range. In this low frequency range, okay, the low frequency range, it has the lesser magnitude, and in the high frequency it is higher magnitude, because body, it's the magnitude plot, it's in dB scale, it's the magnitude, okay, and this is omega, okay. So look at it carefully. At the low frequency the magnitude is being reduced, and in the high frequency the magnitude is amplified, like it amplifies the magnitude. That's why we can say it amplifies the high frequency signal, because the magnitude is more, and it improves the transient response. Transient response means as you go on the transient response, you come to the steady state value. What does the steady state value mean? Steady state means the omega is tending to 0. That's why it is also improving the low frequency and amplifying the high frequency noises. So this is true. Okay. Next, a lag compensator increases the system bandwidth. Okay. We need to look into the lag compensator. So the lag compensator, if you remember, for that the corner frequency of the pole comes earlier to that of the 0. That's why we can see something like this for the lag compensator. Lag. Okay. So basically, what does the lag compensator do? The lag compensator decreases the phase margin. Okay. So that's why the bandwidth gets reduced. But in the question, it was said the lag compensator increases the bandwidth. No, it decreases the corner frequency at the bandwidth. For a typical lead lag compensator, so the lead lag compensator, how does the body diagram look? For the lead lag compensator, it's kind of this. Okay. So sorry, my bad. Lag lead. It's a lag lead. Because first you see there is a lag. This is the lag part, and this is the lead part. Okay. The high frequency components are attenuated. No, because at the high frequency range, this is the high frequency range, the magnitude is more, so it's increasing the magnitude. So this is false. Okay, so if it had been the question of lead lag, so how the plot would have been: first lead, first this lead, then the lag part. We can say in this question, in this part, the high frequency is attenuated, but not in lag lead. I hope so. This was the last question of the day, maybe of the session and of the semester of live session. So this is all I wanted to share this week. So if you have any doubt, you can always, like, regarding these questions or any control system related questions or any robotics related questions, you can always reach out to me in my given mail ID. Okay. So all the best for your exams, and try to solve more and more questions, and keep loving control system. Thank you.